Welcome to this MOOCs online video course Theory of Yarn Structure. In the last few classes we discussed about module 8 related to tensile mechanics of yarns. In the last class we solved the problem of yarn stress and fiber stress and also yarn strain and fiber strain. Also we have started solving numerical problem 5 and we solved for different twist angles beta. If we assume there is no radial contraction of yarn, what will be the ratio of fiber strain to yarn strain. So we solved this column. Today we will continue with solving for the rest of the columns. Let us start with contraction ratio 0.25. So if in this expression eta is equal to 0.25, when beta is equal to 10 degree, so the value of this ratio epsilon L to epsilon A will be 9623. Similarly, when beta is equal to 20 degree, epsilon L by epsilon A will be 0.8538. Similarly, for beta 30 this value will be further less, 6875. When beta is 40 then this value is remarkably less, 4835. In the similar manner we can solve what is this ratio when contraction ratio is 0.5 and there are 4 different angles of beta. These answers will be 0.9547, then for 20 degree beta the answer will be 0.8245, for 30 degree the answer will be 0.6250 and for 40 degree the answer will be 0.3802. In a similar manner we can solve when contraction ratio is 0.75, what is the ratio of fiber strain to yarn strain when beta is equal to 10. This value will be 0.947, for 20 this value will be 0.795, for 30 this value will be 0.56 and for 40 this value will be approximately 0.27. Now if we carefully observe this table, if we go along this direction for a given contraction ratio, when the surface twist angle, when the twist angle increases, this ratio of fiber strains to yarn strain decreases. The same trend is observed here also and here also. Now if we go along this way, for a given twist angle when contraction ratio increases, the ratio of fiber strain to yarn strain decreases. However, when beta is less, this effect is less. When beta is little high as 20 degree, then we see as the contraction ratio increases, same trend is there. However, the effect is little higher. This effect you see when beta is 40, if we increase contraction ratio, the values are changing from say 0.59 to 0.48 to 0.32 to 0.27, remarkable change. So this can also be observed from this data. So, we have solved numerical problem 5. Now, we are going to solve numerical problem 6 of this module. This problem reads as follows: a cotton carded ring spun yarn of 29.5 takes count and 719.43 meter inverse twist. So, you have given T is equal to 29.5 takes and Z is also given 719.43 meter inverse. This yarn is tested for its stress strain behavior. Calculate tensile force utilization coefficient of this yarn, assuming yarn contraction is equal to 0, 0.25, 0.50, 0.75 respectively. So, we have to basically use this expression phi tensile force utilization coefficient of yarn 1 plus eta cos square beta d plus eta tan square beta d. Eta given 0, 0.25, 0.5, 0.75. What is not given is beta d. Now, tangent of beta d is equal to pi times d times z. Z is given, d is not given. What is d? D as we know 4 times root over 4 times t by pi mu rho into z. T is given, rho is a cotton fiber. So, rho we can consider 1.52 gram per centimeter cube. Mu is not given. How to find out mu? Mu we can find out in a manner we learned earlier. Let me show you how. Mu to the power 2.5 by 1 minus mu to the power 0.8 cube q z square c to the power half. Probably we will learn this in module 4. So, it is a cotton carded ring spun yarn 9.61 into 10 to the power minus 8 is the value of q. What is the value of z? Z is given 719.43 and what is the value of t? (29.5) to the power half. So, then you can solve for this expression. You will find out mu will be equal to 0.46. The moment you find out 0.46 mu, then you will come back to this page and you will see what is given 3.14 4 times t. What is t? 29.5. Mu is 0.46 and rho is 1520 kg per meter cube into z 43. So, this tangent beta you will get as 0.5237. Of course, it is dimensionless. So, tangent of beta d is equal to 0.5237, then beta d is tan inverse this value will be coming approximately equal to 27.65 degree. So, in this manner you obtain beta d. Now, you come back to this expression, beta d you obtain 27.65 degree, eta for different values you need to calculate phi. So, phi is equal to 1 plus eta cos square beta d plus eta ln cos square beta d by tan square beta d. Beta d you obtain as 27.65 degree. So, you need to find out this for eta 0, second is 0.25, third is 0.50 and fourth is 0.75. So, you need to find out 4 values of phi, tensile force utilization coefficient in yarn. So, when eta 0, so this vanishes, this 0, so cos square beta d, cos square 27.65 degree, the value will be 0.7864. So, cos square 27.65 degree is equal to roughly 0.7864. When contraction ratio is equal to 0.25, eta is equal to 0.25. So, you substitute 0.25 here, 0.25 here and beta d 27.65 degree, you calculate, you will get this value will be approximately equal to 7597. Now, third one, eta contraction ratio is equal to 0.50. So, you substitute eta is equal to 0.50 and consider beta d is equal to 27.65 degree, beta d is equal to 27.65 degree. You solve for it, you will find out this value will be roughly equal to 0.7278. The last one, when the contraction ratio is 0.75 and beta d 27.65 degree. So, you substitute contraction ratio as 0.75 here and you substitute beta d as 27.65 degree, you will find out this value will be equal to 0.7098. What we see is that for a given yarn where beta d is fixed constant 27.65 degree, for contraction ratio increases, tensile force utilization coefficient decreases. This we see from this numerical problem. So, we solved numerical problem 6 also. So, module 8 ends here. Thank you very much for your attention.